XFL is short for Extreme Function Labeling and is about retrieving function names in a strict binary. This is joint work together with James Patrick Evans, who recently graduated, and Johannes, my PhD advisor. Okay, so imagine you are a reverse engineer and you open up an unknown strict binary. Usually you are facing this situation. Your favorite reverse engineering suite, in this case Binary Ninja, recognizes functions, but due to the symbols being stripped from the binary, the given names are just generic and in this case contain just the virtual address. To give meaningful function names, you'll need your experience as a reverse engineer, and you'll need to spend hours and hours to analyze the code and the interdependencies. And by the way, you'll need lots of coffee on the way. So wouldn't it be nice to have a machine learning model that can produce plausible function names for us? Well, here's XFL, and in this talk I would like to highlight the key aspects that make our whole system work. First, we have created Dexter, a new function embedding that is based on heavy static analysis. We use extreme multi-label learning to predict tokens for a function given the embedding. And in the end, we developed a language model that is able to synthesize plausible function names from the tokens. But what are the tokens I'm talking about? So the tokenization process is the key highlight of XFL. A straightforward approach for function name prediction would just predict the function name entirely. But an obvious downside of this approach, however, is that only names that have already occurred in the training set can be predicted, which contradicts our aim for generalization. Furthermore, in our dataset of 10,000 binaries taken from the Debian packages, we observed that 98% of the function names occurred fewer than 10 times, and 73% of the function names occurred only once. So this makes training any machine learning solution very hard, maybe it's even impossible. So our solution is to split the function names into meaningful labels, into meaningful tokens. And we recognize underscores and camel cases for splitting. We use also a dictionary of English words and common terms in programming. And also we are using normalization techniques from natural language processing. And this way, we are able to map the over 1 million function names in our data set down to 4,096 unique tokens. So now let's take a look at our new function embedding Dexter. We go against the trend in deep learning, which tries to do mostly end-to-end learning with little preprocessing as possible. But here we are emphasizing on manual feature engineering and a heavy use of static analysis. So Dexter consists of 3 parts: a function feature vector, the function context, and the binary context vector. So the function feature vector is created from static analysis and contains, and is not limited to, a vector representation of the control flow graph, locality-sensitive hashing of opcodes, results from a lightweight taint analysis taken from punstrip, and also inter- and intra-procedural features based on the VEX intermediate representations. This list is, of course, not exhaustive. There are many more, and you can find the full list in our paper. So for the function context, we are considering the callers and callees from the function call graph and average all of their function feature vectors into the function context vector. For the binary context, we are averaging all the function features of all the functions in the given binary. We implemented an autoencoder architecture after concatenating all the 3 parts, and we are getting our embedding Dexter as the result in the bottleneck layer, as you can see in the middle. All right, so now we want to predict tokens from our Dexter embedding. And we are using extreme multi-label learning borrowed from the information retrieval community. So our goal is to predict a set of tokens. Please note that this is different from multi-class learning, which only aims to predict one correct label. So when the label space is small, you could get away with learning a classifier for each label, but this doesn't scale very well for us. Thus, we are using pfaster-XML, an efficient tree ensemble-based extreme classifier. You can look up the details of pfaster-XML in their paper, but here I would like to highlight their approach of learning to rank. So pfaster-XML gives us a confidence score for each label. And now we can sort the labels by their confidence score in a descending order and thus obtain a ranking. And now we can use, for example, the top 5 ranked tokens for the prediction, or we could also use a threshold to determine the predictions. To train the tree ensemble, we need a loss function. And we base the loss function on two intuitions. A, the more correct tokens are predicted, the better. And B, the higher the correct tokens are ranked, the better. So let's look at a running example. So let's assume we have as a ground truth set port and error, and we have two predictions, set right error and set error right. In green, the correctly predicted tokens, and in red, the incorrect predicted tokens. As a first step, we can compute the cumulative gain. So we are just counting the number of correctly predicted tokens. So this is not our end goal yet, because here we can see that the two predictions are scored the same, whereby the second prediction, the lower one, should definitely be better. So we introduce a penalty term that penalizes the lower ranked correctly predicted tokens, and thus we obtain the discounted cumulative gain. And here we can see that discounted cumulative gain for the second example is scoring higher, as we wished. So in order to be able to compare different examples, we are normalizing the discounted cumulative gain by dividing by the perfect score, thus getting the normalized discounted cumulative gain. And this very nice property of this is that now the NDCG ranges from 0 to 1, whereby 1 would be the score for a perfect prediction. Okay, so now we got our set of tokens, but unfortunately along the way we lost information about the order. But in order to predict a meaningful name, for example to output dwarf information, we will need to restore the order. So in this example, we have the color make map smooth predictions for a function name, and this is just the alphabetical order and is not a very nice sounding function name. So we want to get this into the right order again. And our intuition is that programmers tend to follow a certain style when naming the functions. For example, having the verb or predicate first, as we can see here with the make, and followed by the object, the smooth color map. So we are modeling the order of Neither nice smoothing, which interpolates the trigram frequencies with bigrams and unigrams. We are also using start and end tokens, so we can recognize that make is actually at the start of the function. This gives us a probability score for each sequence, and we can then use a branch and bound algorithm to find the optimal ordering. So in order to compare against state-of-the-art approaches, we were using the threshold to determine the correctly predicted tokens. And now we can compute precision, recall, and F1. As we can clearly see, XFL outperforms state-of-the-art approaches, Nero and dbin, and also punstrip. To preempt concerns about overfitting on our dataset, we were re-evaluating on Nero's own dataset. And as we can see, XFL still comes out ahead. So the very nice thing about our XFL pipeline is that we can actually change our embedding. Thus, we were comparing against 3 other state-of-the-art embeddings, Palmtree, Safe, and ASM2VEC, and also on different label space sizes, which you can see on the x-axis. We are displaying the information retrieval metrics, and while the 3 other embeddings provide good results, Dexter still outperforms the others by a significant margin. And with an increasing label space, the NDCG here goes down because of the normalization step that is included. So in this talk, I've presented you XFL, Extreme Function Labeling. As a highlight, we tokenize function names into labels. And we introduce our new binary function embedding Dexter, which relies heavily on static analysis. Thus, we can use a scalable function labeling approach. And in the end, we can synthesize function names for strip binaries. So the model and code is available. And thank you very much for your attention. I'm happy to take questions now.
Okay, any questions?
Could you comment on why you think Dexter's embedding is more effective in the context of XFL than the other embeddings?
So we were thinking about how to design Dexter, and we were seeing that many embeddings are actually just using large language models. But we think that the static analysis has to be learned anyhow during the training process, and we think that providing the static analysis by our own will lead to better results.
And the static analysis is unique to Dexter's embedding?
Yes.
This is Joe from Purdue, and it's a very interesting talk. topic. And so I have a very high level questions, like, because I'm thinking about when we do human reverse engineering, we are actually focused on the decompiled code. So I'm curious, why do you not take in those decompiled code into your model input as like more high or accurate result? Yeah, I'm curious about your design choice. Yeah.
So I mean, we were evaluating on many different inputs. So I mean, this is referring to the Dexter function embedding, right?
Yeah. So I'm curious why you choose to learn from the IR code or the Muni code instead of directly on the decompiled sudo C code. Yeah.
I mean, so decompilation code also has like varying quality, and here you're just using the IR because it has been working best for us.
I see. Okay, thank you.
No, great work. Extreme multi-label classification has been widely studied, and there are so many effective models, such as label tree or neural network based. Why do you use P-tree or B-fast tree over than other methods? Thank you.
So we were doing a literature research on this topic, and pFaster-XML just turned out to be a state-of-the-art, thus we were deciding to use pFaster-XML.
All right. I will take the last question. So identifying the functions and giving the name for the function is absolutely useful in reverse engineering, but also identifying the name of the arguments is also very, very useful. Any reasons you think about this approach can be applied to that scenario?
Well, that's an interesting question. Yeah, I don't know an answer like spontaneously, but I could imagine that, I mean, the Dexter function embedding is capturing like caller and callee information, also arguments. So I could guess that you could retrieve information from the embedding there as well. And like then turning also the arguments into labels as target space, I think that could work, yes.
All right, thank you. All right, let's thank the speaker one more time.